Today we try to make prediction about patient no-shows. Imagine that you're a doctor, maybe you're a family doctor, right? Of course, you need to take appointments. Patients will book appointment with you, and they're expected to show up and talk to you on the day of appointment. But in reality, as we all know, people have different kind of situations, right? Maybe they become unavailable, or maybe sometimes people just simply forget. Right? There's always cases where people don't show up, but there may be, something undesirable about no-shows, right? Because if a patient show up, you provide the service, you collect the money. Right? From the service provider's perspective, that's a loss. Right? If they don't show up, you don't get to collect the money. And there may be other consequences, such as the equipment and the resources are wasted, right? So, due to that reason, it's typically important to develop some idea about whether or not a customer or a patient will show up or not. And the same thing goes for other service providers, such as airlines or hotels, right? People book the flight, book the hotel room, but then eventually some of them didn't show up. It's going to be a waste of resource. Okay. Now, that's why we're going to try to study this problem about predicting patient no-show. Right? So we're going to look at the data set as usual. In the data set, basically we will have a target column. That's something we want to predict. But in the training data set and also the testing data set, we need to have information about whether or not certain patients showed up or not, or they didn't show up, right? And then I want to look at the features of those patients to see what kind of patients are more likely to show up and what kind of patients are less likely to show up, right? And so this is the typical tabular data. Again, we're going to use a data frame. So let's quickly move on to Colab. So step one, still as usual, go to Omnitular. And step two, locate this predictive analytics module under lecture materials. And then we're going to use this notebook for classification. Okay, so this is the notebook you're going to see. It's not too different from what we usually do, but there's one small difference. Though this notebook is actually largely already pre-populated for all those cells, because we went through a lot of code last time, and this time we hope to reduce the amount of repetitions, because as we can see, the codes we are doing today is kind of very similar to what we did last time. So this time we're gonna slow down a bit to focus on explaining the concepts in the whole process of using prediction models to make meaningful and useful predictions. Okay, so now question one. For this problem of predicting patient no-shows, if we quickly compare it with the problems we handled last time, for example, predicting the medical charges of a customer, or predicting the house price based on the features of the house, how do you think this problem is different? Predicting no-show, how is that different from predicting costs or predicting prices? Yes, please.
Binary in this case.
Binary, yeah, exactly. So house price or predicting medical cost, for those cases, they are all dollar amounts, right? So it's more like a continuous value, right? So, there's many different possible outcomes. Patient no-show is something we consider as categorical, right? More specifically, it's binary. Only two possible outcomes: show up or not, or they either showed up or they didn't show up, right? Two outcomes. Okay, so this is something we consider as classification problems, where we predict categorical variables. Binary, or sometimes multinomial, like sometimes when we want to predict things like, typical machine learning problems, like if you see a flower, predict which species the flower actually belongs to, right? And for if you were predicting a continuous quantity like prices and cost, and this is typically regression problem, but today we're shifting our focus onto the classification problems. We want to predict categorical variables. Okay? So I have included more examples. If you an internet service provider and you provide several plans, usually a provider that will not provide millions of plans, right? It's only going to be like a few plans. So out of the provided plans, which plan will be chosen? So it's just a few options. And show versus no show, maybe classification of pictures. What kind of animal is in the picture? Is it a cat or a dog or a rabbit? So those are what we consider as classification problems, right? So category variables with only a few options. Okay. For emails, is it spam or a regular email? Okay. So this is the typical difference between classification and regression, and we are going to focus on classification. Now, this is more like an overview of what we did last time. Even though we have a different problem, we're doing classification instead of regression. The whole framework, as we will see, is more or less the same, right? So our approach will be that we're going to build a pipeline. The pipeline will include different steps. Here we have two major steps. Right? First of all, we're going to do something about the data. We are going to do one-hot encoding and also scaling, and those are exactly the same task we considered last time. Okay? And then we're going to choose a predictive model, and here we're doing classification, so we're going to choose a classification model, and then the whole pipeline structure, combine them together to form the combined model, right? So the pipeline is also a model, but it combines the predictive model with some pre-processing steps. And then you'll feed the training data into this framework called a pipeline. You're going to fit the pipeline to your training data, and eventually the fitted model should be able to provide meaningful predictions. Okay? That's the whole idea. A lot of the things are similar to what we did last time. So we're gonna save some details in today's class. Instead, focus more on the conceptual steps. Still, of course, we're gonna see the codes, but for some of the codes, we're gonna just go over them really quickly. And the important thing is to focus on the steps and the concepts. Okay, and let's get started. So if we switch to the notebook, you will find that after outlining the problem briefly and also providing a data set, as usual, through a link to my GitHub repository, we're going to load the data. And this is nothing new. So let's just run this cell, right? So let's use pandas to load the CSV data from GitHub to get a data frame. So let me just run it. It's already included in your notebook as well if you follow the link. Right? So we can just run it and see what happens. And this is a preview of the first 5 rows of this data set. And very simple. Every row is an appointment made by a certain patient, right? So appointment ID is just some identifier of the appointments, nothing very informative. And gender of the patient. Appointment DOW. DOW stands for day of week. So what is the day of the week on which the patient is supposed to show up, right? So it's the appointment day. Is it a Monday or Tuesday or Wednesday, etc. And lead time. Lead time here, lead time means that when you book the appointment, what is the gap between the booking time and the appointment time, right? So you see an integer number here. For example, for the second row, the value is 35. It means that when you book the appointment, you're booking for the appointment 35 days later, right? So the first row is 0. It means that you're booking a same-day appointment. Okay, so that's the meaning of lead time. So that's the time gap between now, when you book the appointment, and the day on which you're supposed to show up. And age, very intuitive, age of the patient. SM as received, so This is like typical these days. Sometimes the provider will send you a text message to remind you you have an appointment on a certain date, right? So this is to show that some patients may have received that text message, but some patients, for various reasons, they didn't receive it, or you didn't remind them. Okay? And finally, we have the target variable, show versus no-show. And the column name is no-show. If you see a yes, it means that the patient didn't show up. It's a no-show. Yes, it's a no-show. If it's no, it means that the patient was not a no-show. Right? So yes is no-show. No is a patient who did show up. Right? So it's a binary variable, yes versus no. Okay? So any questions about this data set? So let me find. So next step is to quickly examine the no-show column. Specifically, we know that there are yeses and nos, right? But how many yeses, how many nos? So this is something we want to handle very quickly. And I think there's some explanation on the different columns, which I just quickly explained. But now here, let's look at this data frame. And let's focus on the no-show column. Okay. And the no-show column, of course, is about yeses and nos, right? So I want to do a value count to count how many yeses, how many nos. So no-show column dot value counts, something we have done before, right? So that gives us the result regarding how many shows and how many no-shows. As we can see, there are 245 yeses, and those patients didn't show up eventually. And 860 no's. It means that they are not no-shows, so they did show up. So this is what we find for the value distribution between yeses and no's for the no-show column, the target column. But by looking at those two numbers, 860 and 245, this can create a potential problem for us to do the prediction. So what problem do you think it can potentially cause? Well, observation may be quite obvious, right? More no's than yeses. I mean, not just a little bit, yes, please.
Overfitting for no.
Overfitting for no, and I think that's the idea is absolutely correct. But why it can cause any potential errors or something sometimes we call overfitting. So what's the problem of having way more no's than yeses? Or if it's the other way around, too many yeses with a very, very few no's, that's also a problem.
It will be accurate for no and then less accurate for yes.
Precisely, right? So it's if no dominates, turn out in many situations, your model can give you outcomes that favors no outcomes. And let's dig a bit deeper. Okay, so the problem is that the labels, the target column, in the content columns, the yeses and nos, we can consider them as labels for the two different classes, yeses and nos, right? They are unbalanced. An unbalanced data set can cause a problem. And why is that? I'll give you hopefully some deeper insight by explaining how the training process of any machine learning model actually works. Right? So we have model in the middle, represented by a box. In our case, this is really the pipeline. Right? And every model is sort of characterized by the model parameters. Like in linear regression, we have the coefficients and an intercept. Right? So the model really maps inputs into outputs. Right? Inputs will be data. Let's say some patient record, and then based on the feature of that patient, you will generate the output, which is predictions. Right? And in the current case, is it going to be a no-show? That's our prediction. Right? So the model is characterized by model parameters, and it maps inputs into outputs. Right? So if we feed training data into the model, what we get as the output will be the prediction based on the training data. Right? For all those patients in the training data, let's predict if they are going to show up or if they're or if they are likely not to show up, right? However, for the training data, we actually observed the actual values in the target column. Right? So no show versus shows. That's what we already know for the training data. So we're going to compare the predictions made by the model on the training data and the actual outcomes in the training data. So what we are interested in for most predictive models is the gap. I want it to be accurate. Want the prediction by the model to be very similar, very consistent with the actual observation. Then we have a small training error. Right? So we're going to compare those to get some idea about the training error. And then remember, the models are characterized by the model parameters. Right? I can actually change the model parameters and observe how the training error also changes. Right? So what we want is actually to adjust the model parameters in a way such that I can reach the lowest level of training error. Right? So the target is really that I will adjust the model, adjust its parameters in order to minimize training error. In the current case, the training error is the discrepancy between the actual outcome, show versus no show, and versus the predicted outcomes. Right? So that's how the training process works for most predictive models. And coming back very quickly to this problem, right? We want to minimize training error, but if there are so many more no's than yeses, imagine that the model can simply take a very simplistic approach. Let's say the model decides to label everything as no yeses. Every time I give it a record, it will tell you that it's a no, right? The patient will not be a no-show. Right? In that case, at least for the training data part, it will be correct for 860 records. Right? It will be wrong for 245 records. Right? So what is the accuracy level? Well, it's going to be 860 out of the total number of predictions on the training data, which is 860 plus 245, which is approximately 78%. Right? I mean, 78% may not be that impressive, but you know, you let the model almost do nothing, just to predict everything as no. And then you're already achieving 78% as accuracy. Right? So if you only focus on the accuracy as the performance measure, it's not that bad, right? It's not, I mean, very impressive, but it's not that bad. However, with this sort of, I guess usually 70%, you will consider that as something like maybe acceptable or reasonable, but the model is useless, right? Because you ask the model to predict everything as no. Right? It's not informative at all. So with unbalanced data set, sometimes during the training process, the model will simply try to favor the majority class, which is no's, no's here in the target value, because there are so many no's, right? So it could be possible that simply eventually to label most of the data points as no's, and turns out the model is actually useless, right? So if you have unbalanced data, that's the potential problem. So that's why we typically want to avoid the situation of have very unbalanced outcomes in the target value, in the target variable. Okay? Questions about that? All right, so what do we do? Now we have an unbalanced data set, and that's what is given us, right? So what would you suggest to do? I mean, apparently we want to convert the unbalanced data set into something like a balanced data set, but what can we do about that? Yes, please.
Focus on no's and be like no and then not no.
Can you be a bit more specific? No's and focus on no's. We have 860 no's, right? So what do we do? The problem is that we have too many no's compared to yes.
You can either shrink it down to meet yes.
Exactly, right? So one quick solution is that we have too many no's, much more than yeses. How about I reduce the number of no's How do we reduce this? It's something called undersampling, right? So let me quickly show you an illustration. So we have, let's say the nodes are represented by blue balls and yeses are represented by red balls, right? So now this is actually just an illustration. It's the numbers apparently different from the numbers in the data set, right? But let's say we have 3 yeses and 8 nodes. Too many nodes, too few yeses. So very simplistically, how about focusing on the nodes? If you have too many of them, just randomly throw away some of them. Okay, there were 8 nodes, but let's randomly throw away 5 of them. So now I'm left with 3 nodes, and this is called undersampling. Okay, and then I throw away some of the nodes, and it leads to a balanced data set if you combine the red balls and blue balls in this case, right? Because now it's balanced. Like each color will have exactly 3 records. Right? But you're throwing away data. Sometimes this is not desired because this is reducing your data size, right? I mean, we constantly talk about big data. We want to have as much data as possible, but now you are throwing away data. You are throwing away information. This may potentially cause you some loss in terms of the predictive outcomes as well. If we can undersample, what's another possible approach without throwing away any information? If we can undersample, I think we can also oversample, right? We focus on the minority class, the yeses, only 3 of them here. Can we find a way to expand the 3 yeses into 8 yeses? And then we have 8 yes records versus 8 no records. Again, we will have a balanced data set. But how can we possibly create 8 yes records from the 3 that is already in the data set? So what do you suggest? How do we do oversampling? How do we create a balanced data set to get 8 outcomes out of 3 yeses? Any suggestions? Well, imagine that I draw this dashed box. Let's say imagine that it's a bin or a basket, right? So I'm going to put 8 red balls, 8 yes balls in this basket. And then later I'm going to combine the 8 red balls with the 8 blue balls so we have a balanced data set. Right? But how do we do that? It's something called sampling with replacement. And let me quickly demonstrate how it works. Right? So let's say I take one ball out of the 3 available balls. Right? I mean 3 yeses. Let's take one of them randomly. So let's say I took the number 1 yes ball. Right? So it's the first record that has yes outcomes. Right? And I get one ball in the basket. Normally, if you take one ball from the total 3 of them, and then you will be left with 2. Right? But we're doing something called sampling with replacement. So after I've taken away the first red ball, let's say we replace it with an identical ball. So we're still left with 3 balls. Right? So this is why we call it sampling with replacement. Now I have 1 red ball in the basket. So let me do the second, right? Again, this is exactly the same simple procedure. 3 of them, 1, 2, 3, I take one of them randomly. And this time, let's say I took the second red ball, right? So yes ball number 2, we can call it yes ball number 2. And we didn't actually remove it. Let's imagine that we're replacing it with an identical number 2 yes ball, okay? And then keep going. Let's do another random draw. Let's say we again take the yes ball, and then one more red ball. So we have 4 red balls, and keep this process going on. Eventually, we can always get 8 red balls, right, by repeatedly draw something from the initial available 3 red balls. Right? Now I have a basket of 8 red balls. Those are yes outcomes versus the original 8 blue balls. We put them together, we'll have a balanced data set. Right? Of course, we'll have some duplications, right? Because how can you create 8 records from 3 records without duplication? That's not possible. Right? So you look at the red balls after oversampling, there's quite a bit of duplications. Right? We have 3 number 2 yes records, we have number 3 yes records, and we have 2 number 1 yes records. But that's okay. Okay, so we can allow duplications in this context. Okay, so we put them together, we should be able to create a balanced data set. Okay, so let's go back to the notebook and let's implement this idea. Okay, so we're going to deal with oversampling, and we just explained the idea. There's also some notes in the notebook, but let's actually first separate the no's from yeses. Okay, so we have DF, the data set, that contains everything. Right? Now, first step is that I want to create something called DF no that only contains the no records. Okay, and that's achievable by something we've done before, which is filtering. Okay, so as you can see, Gemini already provided the hints, so let me just accept it. Okay. For the original data set, I will select based on the condition. Right? So the first condition is to select those has their value in the no-show column equal to no. That's the condition. The highlighted part is condition. Right? And then use the square bracket to do the filtering to only filter out those records where the no-show value is no. And similarly, I create a second data frame called df yes. For df yes, I'm going to use the condition of the no-show value equal to yes. Okay? And then use filtering to select only those records with the target variable equal to yes. And that will create me 2 separate data frames, which is basically split the original data frame. Okay? And then we know that we have no's in total of a total size of 860 and yeses of a total size of 245 or 46. Anyways, so let's do this. So number of no's equal to length of df no, and number of yeses equal to the length of the df yes data frame. Right. So this is just to count how many records having no values for the target variable. How many of them have yes values? Right. So eventually, let me just try to view the values of no's and yeses. And not surprisingly, it's 860 and 245, right? As we already know. But then in this way, df no, df yes, they only contain no and yes outcomes based on the target value. Okay? Now, we're going to focus on df yes, because we're going to do oversampling, right? We'll focus on the minority class. Sorry, I should select df yes here. Okay, so it has 245 records. I want to augment it, right? So how do we do this? And this is where we use a command or a function called df, and then we focus on yeses, right? The minority class. Dot sample. How do I sample? Well, I need to decide how many samples do I want to create, right? I want to create 860 samples because that's the size of the majority class. So n equal to 860. But of course, what I actually want to do is to let it equal to the number of no's. So we have a variable for that, right? And no is the number of no's. Okay? And remember we mentioned this concept of replacement, sampling with replacement. So we're going to do replace equal to true. And this actually, replace equal to true, that will allow you to do sampling with replacement. Okay? So finally, there is something called random state. Because it's a random sampling, right? So it's typically you don't have any control, it's completely random. But sometimes you want to be able to reproduce what you sampled, right? So next time, if you use exactly the same seed number or random state number, let's say 18, and then you will get exactly the same random records, right? If you use 20 or any other different number, you will get different random samples. Right? Anyways, this creates another data frame that is sampled from the yes data frame. And then I created 860 records from the original part of the data with yes values, right? So n no is 860. And let's give it a name. Let's call it df yes OS for oversampling, right? So this is the oversampled data frame. And we can, after that, we have done this, so let's just quickly preview the oversampled data frame. All right, so first of all, the row indexes are completely messed up because you are randomly taking the rows from the original data frame, right? So it's not guaranteed that the first row is sampled as the first record in the oversampled data set, right? So it's all messed up. And let's scroll to the bottom. Now we can see that after oversampling, the data frame we created now have 860 records. Okay? And if you look at the labels of no-show, they are all yeses, right? Because we actually focused on the minority class, which is the yes records for patient no-shows, and then augmented to 860 records. And they're going to be duplications, even though we cannot see that very clearly. But whenever you are trying to do sampling with the replacement, you always have duplications. Okay, questions about this? All right. Going back to the slides. Now, we have created two data frames. The no data frame is actually the original data frame, but only for the part with no records for patient no-show. Right? Now, for yes records, we didn't have as many records, but we augmented it. Now we have balanced data set. Right? We have a oversampled yes data frame and the original no data frame. So the next step is to put them together to form the balanced data set. Okay? And this part is pretty straightforward, but we're going to use a function I believe we haven't used before. So basically, it's very simple. It's got pandas.concat. Concat means concatenation, right? To put those two data frames together to form a new data set. And what do we concat? It's a list of two elements, yes data frame after oversampling and the original no data frame. So just put them together by using this concat function. So this part is actually, I guess, pretty straightforward. So let's just do that. So this part we're going to, in notebook, actually, I intended to do something else, right? So for the df yes OS, focusing on the no-show column, we can do a quick value count. And just to quickly demonstrate that indeed we'll have duplications. Oh no, sorry. Don't focus on the no-show column because they are all yeses, right? Focus on the appointment ID because we want to see the original appointment ID. Originally, they're supposed to be unique, right? I mean, if you check that, it would be unique. But then after oversampling, you will see that they're not unique, right? For example, this number here, 5642785, there are 8 of them, right? So it means that original appointment was repeated 9 of them, repeated for 9 times. Okay, so that's sort of expected. Okay, but next we're going to use pd.concat to combine the oversampled yes records and the original no record part. Okay, so it's pd, that's pandas, concat. Concat means the concatenate, right? And a list of 2, df yes, but oversampled, and df no. And then we can quickly give it a name. So df OS, oversampled data frame, but it's combined for both yeses and nos, right? So df OS. By putting them together, let's quickly examine the number of rows. It's 1,720 rows, right? It's twice of 860, right? So now, after oversampling, the yes part has 860 rows. Combined with the original 860 no records, we have 1,720 rows. So that's the balanced and combined data set. Okay? So that's actually one of the focal point of today's class, because for the remaining part, it's going to be more or less similar to what we did last time. Any questions so far? So basically, this is oversampling, right? So if you want, you can try undersampling. We lose some data, but it also serves the purpose of making the data set balanced. Now, what we're going to do is already moving on to deal with the data. It's something we did before. So we first want to separate the data into X and Y. Right? X is the features, Y is the target, which is no-show. Okay, so then that's the first split. We're going to do the train test split. After those two splits, we're basically going to be ready for feed the data into the pipeline we're going to build. Okay, so this part, I think I don't intend to spend much time on it. So as you can see, I already included most of the codes here. So X is to focus on the oversampled data frame, which is balanced. Right? But I will drop the target column, no show. I will drop the appointment ID column because that's not going to be providing any useful information for doing prediction. So for X, I'm dropping those two columns, and the remaining columns will be treated as the features of the patients. Right? Later on, we're going to predict based on the features. So this is the X. And Y, how do we do Y? We can do DF over OS, because from now on, we always focus on the balanced data set. And we're going to, typically we're going to select no-show, right? This is the target column. But there's one small caveat. So what do you think is this one small caveat if we just directly select the no-show column? Something I believe quite simple, right? If you look at the no-show column, yeses and nos, right? I don't want to have textual values because, I mean, eventually all the computations will be based on numerical values. I want to convert them to numerical values. So let's convert no to 0 and yes to 1. Right? Typically, yes is considered as some positive outcome, and then that's represented usually by 1. And no is negative, and that's actually represented by zeros. I want to convert it into zeros and ones. So there's a simple way of doing it. So we're going to do some simple mapping. How do we map? Well, we use a dictionary structure, but the idea is pretty simple. So yes will be mapped into 1. Okay? And no's will be mapped into 0. So we take the no-show column, but then we want to map yes into 1 and no into 0. And that's our Y. Okay? So let's display both X and Y. First Y, then X. Let's see how it goes. Okay, and for no-show, I mean, so for Y, this is the display of Y, right? So we see 1 and 0. 1 is yes, 0 is no. Okay, so that's something that fulfills our purpose. And then the second display is the, the feature part, the X part, right? So then we can see that we only have those useful information, useful columns. We excluded the target column, which is no-show. We also excluded the appointment ID because they are not going to provide any information. All right, so this is how we get the data a bit more ready for the subsequent steps. Questions? Now, the next part, this is the splitting into features and target, right? After removing the column that will not be useful, splitting into X and Y. Okay, so I provided the Python command here as well, but it's already in the notebook. So we have X and Y, feature and target variable. The next step is to do a train test split, right? So remember that we want to use part of the data as training data so that we can adjust the model parameters to get a model that can perform well on the training data. Okay? And later on, we're going to use the remaining part of the data as testing data to test the performance of the model. And for this part, train test split, it's more like a horizontal cut, right? So let's say the top part above this horizontal line, above this horizontal cut will be training data, and the remaining data will be reserved for testing performance purposes. Okay, and this is a train test split, and then eventually we do this split for both X and Y, right? So we'll have X train, X test, those are training data of the features, and Y train and Y test for the training and testing data for the outcomes. Okay, and for this part, something we did before and already include the code. So I will just maybe briefly explain it without going into much details. So, you need to import the module train test split from a submodule inside sklearn. So this is called model selection because this is eventually for testing performance purposes for you to select model, right? And then we create X train, X test, Y train, Y test by using train test split. We split X and Y and test size equal to 20%, right? We need to reserve 20% of the data as test data to be used later on, and 80% will be used for training the model. And random state 42, and you can use different number as long as you keep that number in your record, right? So next time I want to replicate exactly the same split, I just use the same random state, right? This is nothing too important. All right, so I included this ytrain.value count to have some overview of the distribution of yeses and nos or zeros and ones in the training data, right? So let's run this cell without spending too much time on it, right? So basically, the outcome is that we have zeros and ones, 695 zeros and 681 ones. So 0 is a no and 1 is yes, right? As we can see, it's slightly unbalanced, right? I mean, we did do balancing by oversampling before. Why now this part is again unbalanced? Any thoughts? Remember, we converted the data set into a balanced data set, right? But that's the whole data set. Now I randomly split that into two parts. And this result is for the training data, the training data part of the target variable, right? After split, of course, it can be unbalanced again, right? So, but usually it's okay because it's a random split. Even though it's not going to be perfectly balanced, but then by doing a random split, there will be just a small differences, right? Because you're doing random split, the outcome is usually that the number of zeros and number of ones are still similar to each other. Right? If you want them to be strictly equal to each other for the 0 values and 1 values, there's some controls you can do called the stratify equal to the target variable y, but let's save that because I don't think usually that causes a huge problem. Okay, so any questions about this? This is still getting things ready for the training. Okay, splitting into X and Y, and then vertically splitting into training and testing data. Now, later on when we train the model, we're going to use X train and Y train. Right? The training part of features and the corresponding target variables. Okay. And let's use a couple of minutes to proceed a bit further before the first break of today's class. Now we're ready to build a pipeline. As last time, we're going to include two main steps. It's two main steps in the pipeline. First of all, we're to do some pre-processing. Right? So we want to scale those features. I mean, the numerical features, we want to scale them so that they have a similar scale, so they don't have asymmetric power in terms of affecting your outcomes. We have the one-hot encoder for the categorical variables in the feature variables, like gender, male or female. I mean, they're not directly usable, right? We want to convert them to binary values. And something we did last time, so we won't spend much time on that. But the idea is that we're going to define column transformer. And for the categorical variables, we're going to convert them to binary values by using one-hot encoder. For the numerical values, because the scale will be different, right? So age is apparently having a much larger scale than number of whether or not the text message is received, which is binary value. So we want to scale them. So for this part, let's go over it very quickly. So the first step is to define the categorical and numerical, columns, right? So I'm just splitting the column names into two groups, two lists. So cat columns and the num columns, those are for categorical and numerical column names. And then this part defines the column transformer, and there's some library to import. I guess, I mean, as long as when you are doing it, you can look up or ask ChatGPT or do whatever to get the correct module to import from. That's okay, right? And inside the column transformer, we specify what kind of transformation we want to do. Okay? So for the cat columns, the categorical columns, I do the 100 column, and I call the step cat. You can call it by any other name. Right? For those numerical columns, we're going to use standard scalar, and this step is named as num. You can use something different, any text or string value you want to use. And the remaining columns, you can either pass through to do nothing, or you can drop them. And here it doesn't make any difference, right? Because we're considering transforming the feature columns, and then any feature columns is either inside the numerical columns or categorical columns. So there's actually no remainder. So then you can choose either drop or pass through. It doesn't make any difference. Right? So this is what we did last time. So let's not worry about the details. And you can always go back to figure out the details by looking at the codes. So I have run it, and then the column transformer is basically defined. Okay, and then we can define the model. Okay, so the model here is going to be a classification model. Before we use the linear regression model to predict house prices or medical costs, we said that's only for continuous variables. So question, why is it not a good idea to use linear regression to predict no-show outcomes, 0 or 1? So why is that? Because linear regression predicts based on linear relationship, linear function. Right? A linear function is not guaranteed to always be inside the range between 0 and 1. Actually, ideally, we want exactly 0 and 1. Okay? But for linear regression, it's not even guaranteed to be bounded by this range, because the linear function actually grows very quickly if you increase the inputs. Right? So that's why it's not guaranteed. A better idea is actually use something. There are a bunch of methods for classification, but the one we're mentioning is the logistic regression, at least for now. The idea is pretty similar. We have no-shows and shows, 0 and 1, 1 and 0, right? So two outcomes, but then it's actually typically not that easy to directly find out a relationship that can map feature values into binary values precisely. Right? So instead, this method, logistic regression, will focus on the probability of a record being possibly yes or being possibly no for no-shows, or 0 and 1. So basically, we model the probability of the outcome value, no-show versus show, equal to 1, based on the features using this functional relationship. It's quite, relatively complicated, so we don't worry about the details. All we need to know is that this function will give you values between 0 and 1. And we treat that value as a probability, right? If, let's say, the model predicts a value of 0.4, it means that with 0.4 or 40% chance, I predict the outcome to be 1, which is a yes for no-show. Okay, so that's the main idea. And in terms of implementation, it's actually quite easy. So let me show you quickly, and then we can have the break. Okay. So I already included codes here. Just a very simple one-line code, excluding the importing command. So we import logistic regression. It's again in the module of linear, because if you dig deeper, it's actually based on a linear relationship between inputs and outputs, but you first further transform the linear relationship into a nonlinear function. But the details are not so important. The important thing is that we can simply define the model by using the logistic regression function in the corresponding module, and the model is built. Right? And the next step will be to combine the column transformer and the the logistic regression model we just defined into the pipeline, and then we can train the pipeline. We have done the logistic regression part and also the preprocessor part. And this part is about the pipeline. The idea is pretty simple, just combine the two together, right? And specifically, if you look at the syntax, which is not super important here, but it's actually also very clear, I believe, and intuitive. So when constructing the pipeline, we simply tell Python that we have two steps. Right? In the pre-processing step, and this part is the name, pre-process is the name of the first step, we're invoking the column transformer. And then the second step is where we have chosen the classification model. And what we have done is to include the logistic regression model. Actually, in this notebook, we have already defined the model. So let's just change the task in the second step into model. But instead of directly using the logistic regression function, the outcome will be the same. But in this way, later on, when we switch to other tasks, we can simply change. How we define the model. Right? Now, let's run this cell. And as you can see, the output of this cell is simply to display the content for the pipeline. I call it pipe. So basically, this is the structure of the pipeline, right? So in the dashed box on the top, what we have is the column transformer, including how you would transform the categorical variables and how you would transform the numerical variables. And the second step is to use the logistic regression model, and you put them together, you'll form a pipeline. And now you can actually use the pipeline to do training and further do some prediction. Okay, so how do you train the pipeline? Well, it's pretty simple. You just use pipe.fit, and you fit it on the training data. So you're going to use xtrain and ytrain, which is the training part of the data. So one thing actually somehow interesting, if you look at the color on the screen is not exactly right, but if you look at your own notebook, it's somehow the color of all those steps, all the different components here are somehow light orange color. If you see that color, it means that the model is not trained yet. Okay, and then we're going to fit the pipeline. Again, one simple line of command, which is pipe.fit on the training data, and let's run it. And now you see that the same structure shows up, but the color is different, and it's a light blue color. Usually that color represents that the model is already trained. Right? If the model is already trained, the next step is that you can use the model to really make predictions. Okay, so that's how we can construct the pipeline and fit it to the data. So that's two simple steps. Now, if it's trained, it's fitted, and then we can actually move on to make predictions. Right? So usually you want to predict for a new data record. So for example, you have trained the data on the training data, but now let's say another patient showed up, booking an appointment. So let's say that patient is a male patient, right? And he got an appointment on a Tuesday, so that's why appointment DOW, day of the week, is Tuesday. And lead time is 30, so the appointment is 30 days later. And then the age of that patient is 50 years old, and SMS received is 0, meaning that we didn't remind the patient for the appointment. We won't remind the patient for the appointment. Okay, so this is a new data record. So we want to somehow convert that record into a data frame, and then we're gonna give the data frame, which represents a new patient record, to the fitted model, which is the fitted pipeline. And the pipeline will tell me whether or not that patient will be a no-show. Okay, so let's try to do a quick implementation. Okay, so first of all, we need to define this record, right? So it's going to be a new data point. So let me just call it new data for simplicity. Okay, and then before we do that, actually it may be helpful if we look at X-train, the training data, dot columns, because the way you define the new data point as a data frame is to specify the values for the different columns, right? So let's convert that to a list to better visualize the columns inside the training data in terms of the patient features. And then I'm going to construct a list that gives every column a value, right? So let's call it new data. And new data is going to be equal to a list. So gender, let's say that's male, so M. Okay, and then appointment DOW, that's going to be Tuesday. And lead time, as we mentioned, it's going to be 30, right? So let's say the appointment is for 30 days later when the patient is trying to book the appointment. And age is 50. And SMS received is going to be 0. So let's say we're not going to remind this patient. Okay? So this defines this new record as a list. And let's further convert that into a data frame. Okay? So let's call it df new data equal to pd.dataframe. And that's how we construct a data frame. Okay? And the content of data frame is going to be the new data, because new data is a list that represents a patient, right? I mean, more generally, you can use two lists to represent the features of two patients. And then what we are giving to pandas data frame is a list of patient records in the form of lists, right? So that's why we see the square brackets, because I'm providing a list of patient records. It just happened to be the case that we're only providing one patient record in this case. So it's a list of one patient and convert that into a data frame, okay? So, but then we won't have the column information by simply doing this, right? But what we can do is to specify columns equal to X-train dot columns, right? Because the training data X-train is actually a data frame. It has all the column header information, right? So in this way, we're creating the new data frame and call it df new data, okay? And then we can quickly visualize that before we move on to do the prediction. Sorry, the typo. Columns. Anyways, so this is creating a new data frame representing a new patient, right? And then for this patient, I want to find out what is the likelihood of the patient being either a no-show or not a no-show, right? So how do we do that? Well, remember we have fitted the pipeline, right? So pipe is the name of the pipeline we defined. We have fitted, so we can use it to make prediction. So pipe.predict, it can be used to predict the outcome for this new patient. But before making binary predictions, let's actually do a probabilistic prediction. Let's do pipe.predict proba. I mean, this is the syntax for doing probabilistic prediction, right? So instead of giving you directly the class label, no-show versus show, we're trying to figure out how likely that patient is a show or no-show, right? So what do we predict? Well, we predict based on this new data frame, df new data. Okay. So the outcome should be showing you two values. It's actually something like an array or a list of similar things, right? So as we can see, we have two values. The first value is 0.38. The second value is about 0.62. Okay. Now remember, we have labels being 0 and 1. Right? 0 is, of course, the first label because it's smaller than 1, and 1 is the second label. So those two values, if you look at it closely, they add up to 1. So they're really representing probabilities. Okay? The first value, 0.38, means that the probability of that new patient to be 0, which is a show, right? 0 means that patient will show up. That probability is about 38%. Okay? And the remaining number, which is 62%, that's the probability of the patient to be predicted by the model as a no-show. Right? The model thinks that with 38% chance, the patient will show up. With the remaining 62% of chance, the patient will not show up. Right? That's 0 and 1 as the label of the target value, target variable. So, question, this is the probabilistic prediction or estimation of the no-show versus show chances. But if you have to make a binary prediction, right, if you want to tell or predict whether or not the patient is 0 or 1, what would you do? Okay. So those are the probabilities. 38% chance the patient will show up, 62% chance the patient will not show up. Then if you have to do a binary prediction, show versus no show, what do you choose? Show or no show? So everyone getting the idea? So first do probabilistic estimation, right? So 0, the first one is 0, the second one is 1. So the show chance is 38%, no show chance is 52%. Right? So I think, intuitively, I will predict the patient to be a no-show. Why is that? Because no-show has a higher possibility, 62%, higher than 38% for the patient to be showing up, right? So in those cases, typically, or by the convention, I will predict the patient to be a no-show. However, of course, in reality, it's really based on how you choose the threshold, right? So let's say the default threshold is 50%, right? If the chance is more than 50% for not showing up, it's a no-show. Right? But it's always possible that they said, I want to be a bit more conservative, right? I don't want to easily predict someone to be a no-show. Let's say only when the chance of this patient being a no-show exceeds 70%. Only then I want to classify the patient as a no-show, and then I will predict show instead of no-show. Right? So intuitively, we will tend to predict that patient as a no-show, but it really depends on how you determine the threshold. And the threshold is something we consider as a hyperparameter. Right? You actually decide the threshold first, and then you use the threshold to generate meaningful outcomes. Right? I will come back to this point later. So now, this is actually your prediction in a probabilistic way, right? So next, let's actually do a binary predict. So this time it's even easier. We just say the pipeline, we fit it, dot predict, and we predict based on the new patient data point. And what do we have? It's an array, but the value inside the array is 1, right? It means that I predict the patient to be belonging to class 1. And what is class 1? Class 1 is yes, right? Yes means that's a no-show, right? Because the target column is no-show. And if it's yes, no-show, then the patient is going to be a no-show. And as we can see, those two predictions, probabilistic versus binary prediction, in this case, they are consistent, right? Because the chance of no-show is greater than the chance of showing up for the patient, by the patient, then it's going to be predicted as a no-show, right? But of course, like if you want to be conservative, and then it's a different story. Any questions about that? All right, so that's how we can, do prediction based on a new data. And I'll have the same information in the slides as well. Now, the next part is to evaluate the performance, right? We fit in the model, now it's capable of making predictions. How do you know it's a good prediction? It's a good model for making more or less accurate predictions, or sometimes it may not be such a good prediction. So how would you suggest to evaluate the performance of the model? Right? If a model, it's fitted, it's trained, now you can make predictions. But are the predictions going to be good or bad? How do we tell? And that comes back to the train-test split, right? So training is performed based on the training data, but we haven't used the testing data, right? So now we move on to the testing data, and we want to first predict on the testing data, and then we compare the prediction on the testing data with the actual results of the target variables in the testing data to do a comparison, right? If the gap is small, it's good. If the gap is large, it's not good. And the concept is actually quite simple. Okay. Now we're going to predict based on training data, and this is the probabilistic prediction. If you do predict underscore proba, it's going to be giving you the probability values for each record, right? So it's an array. You can think of it like a table or a matrix. Each row corresponding to one patient in the testing data set. And as we can see, for the first patient in the testing data set, the zero or show chance is 78%, and the no-show chance is 62%, which is rather similar to the example we have just seen. Okay, so this is the probabilistic prediction, but we can also do the binary prediction on the testing data. It's a bunch of 0 and 1 values, right? So each 0 and 1 is corresponding to one patient record in the testing data set, and we're simply predicting the actual outcome, show versus no show, or 0 versus 1, right? And this is how I call it Y predict. So we only need to keep in mind for now that Y predict is now the predicted labels in the testing data set. I want to compare that with the testing label. So this is actually similar to what we have done before, but for classification problems, it's going to be slightly kind of different from regression. Regression is more straightforward, right? We just have the predicted values. You calculate the gap and take the average based on how many records you have, and that already measures how good it is. And that's actually usually something like mean square error we used last time. It's a similar idea. Or if we use R squared, that's another measure. But for classification models, we actually have more metrics to be discussed. Right? But before that, just a very quick recap of how the testing process works. Right? Again, the model, you feed test data into the model, it will provide predictions based on the testing data features, and then you want to compare with the actual class labels in the testing data, and then you want to measure the gap, right? And the gap will tell you about the testing error, often in the form of accuracy, alongside with a few other metrics we're going to discuss, right? Now, one important point. Why do we test the performance based on the testing data instead of the training data? Because you build this model, you predict based on this model, and the final purpose is that whenever for future patients booking appointments, I want to predict the outcome of those new patients, right? And this is the future. The future is not seen by the model because it's in the future, right? So if you are testing the performance on the training data, that's something, some sort of cheating, right? Because the model actually tailored itself to best fit the training data. It has already seen the training data, so you cannot further use the training data to simulate what happens in the future. Instead, the testing data was reserved during the training phase, so it's somehow simulating the future because it has not been seen by the model. Right? So that's the idea of using testing data to test the performance. Now, as mentioned, this is the testing data. You already observe the actual outcomes for show versus no show, but then you apply the model, you can predict for all those patients in the testing data set regarding whether or not they are going to show up. Right? So you have the actual outcomes, you have the predicted outcomes by the model. You can compare them to figure out the discrepancy. Right? If they are consistent, you have a good model. If they're not consistent, you don't have a good model. The idea is pretty simple, right? But when it comes to actual performance, it's actually going to be slightly more complicated than what we just described, even though the essential idea was the same. Okay, so this part we're going to introduce two functions that gives you different performance metrics. The first function is called confusion matrix, and the second one is called the classification report. They provide a bunch of performance measures that tells you about how good or bad your model is performing. Okay, so let's import those actually to functions. So the first one is called confusion matrix, and the second one is classification report. Both of them are from the sklearn.metrics module. So let's do CM, confusion matrix, equal to confusion matrix. And the arguments for calculating confusion matrix will be y test and y versus y prediction, right? So because everything boils down to comparing the discrepancy between the tested data and also the predicted values on the tested data, right? So we want to compare those two to figure out the discrepancy. And another is called the classification report. Let's call it CR. And again, just to simply use this function, classification report, we have imported and to compare test and prediction. And then we can print out the results and to see what is included. Okay. Actually, let's do it one at a time. Let's first print out the confusion matrix. It's a 2x2 matrix, right? For binary classification, it's 2x2. If you have multiple classes, it's a multinomial classification, then you will have more rows and columns, right? So here we have those 4 numbers here, and we want to figure out the mean. Okay, so let's quickly go back to the slides. I have an example in which I use the slightly different numbers, but the idea is essentially the same, right? So this is a similar 2x2 matrix. I put different numbers there, but the idea is the same. Now, for this matrix, if I tell you that the row indexes represent reality, what happens in the reality, and the column indexes represent your prediction, can anyone suggest some ideas about how to interpret all those numbers in this confusion matrix? And how it reflects how good or bad your model is. Any suggestions? It's actually quite intuitive. So we have 4 numbers, right? Let's look at the top left number. So it's for the label 0 in reality and also label 0 for prediction. It means that there are this many records, 3,441 records. You predicted them as zeros. I mean that they actually showed up, right? They are shows. And in reality, they are indeed zeros. They indeed showed up, right? So this is something sometimes we consider as true negative, right? You predict them to be negative values, which is that patients show up. And in reality, they indeed show up. If you see a large number for this entry, it's good, right? Because it's a true negative. You are correctly predicting some patient to be zero, to be shows, right? Now, in contrast, if you look at this number here, 2003-04, right? It represents, in terms of prediction, the model predicted as 1, no show, right? And in reality, it's also 1, looking at the row index and column index, right? So 2003-04 patients were predicted to be 1s, or no shows. And they were indeed no shows in reality. So that's also good. You see a large number here in this entry, in the lower left part, it's also good, right? Because the prediction is the same as the reality, which is good, right? And then for the remaining 2 values, for example, this red number, if this value is bad, is large, then it is not good. Why is that? Well, if you see this number here, 1,379, it means that there are this many records predicted to be no-shows. But in reality, looking at the row index, they actually showed up. It means that you made a mistake, right? So sometimes we call this false positive, right? Because the prediction is positive, which is 1, but in reality, they are 0, negative. So it's false positive, right? And similarly, this number, the purple number, 2083, right? You predicted them as zeros, as negatives, but then in reality, they are 1s, they are positive. Right? Again, you made a mistake, but the mistake type is different. So this time we're making actually what we call the false negatives, right? Because they're predicted as negative, zeros, but in reality, they're actually positive. They are no-shows. Okay, so I think the idea is pretty simple, right? But I think the expectation is that we should be able to interpret those numbers if you are given such a matrix. And sometimes, I mean, for some simple calculations, it may be possible for you to answer questions that like the accuracy, right? How many records were correctly predicted? What's the top left plus bottom right, right? Versus how many records were incorrectly predicted? It's the top right and plus lower left, right? So there's a bunch of things we can do, even though it's just a simple structure showing us like false negatives, true negatives, and false positives and true positives, right? So there's some explanation here, but I believe the idea is not too intimidating, right? So then this table here summarizes actually the meaning of every entry in this matrix. But of course, like on the right-hand side, this is a generalization to multiple classes instead of binary prediction, right? So you can have like a total of 4 classes, and then you will have a 4x4 matrix. And then, for example, the entry here, where my pointer is, will be representing something you predicted. Maybe let's switch to a different cell. So this entry here is something the number of records you predicted to be class 3, but in reality they are belonging to class 1, right? Anyways, I think this is rather intuitive, but do we have any questions? All right, so this is the confusion matrix, right? And there's also the classification report, which contains quite a few metrics, and let's take a look at it. So this is actually, I guess it's not difficult, but sometimes it's confusing. So I mean, you don't have to memorize everything, but just to figure out the meaning based on either the codes or the generated outcomes is going to be good. Now, this is the classification report. It contains several metrics. So it has precision, recall, and F1 score. It also has accuracy and also the averages. So there's quite a few things going on. Let's try to figure out the meaning of all those entries. Okay, so let me try to do some annotation. All right, so let's look at precision first. And you'll find that for precision, there are 2 values, right? So 0.59 and 0.65. I mean, that's corresponding to labels 0 and 1. Okay? The 2 values can be interpreted fairly similarly, but to get started, let's focus on this number, 0.65. And that's the precision for the label 1, or the precision for no-shows, right? Because 1 means no-show. So the precision for no-show is 65%. What does that mean? And actually, we have a formula for that. The formula of precision is here. Okay, it's true positive divided by true positive plus false positive, right? True positive plus false positive, that's everything predicted to be positive. Right? Either it's correct, so it's true positive, or it's incorrect, so it's false positive, right? So the ratio specifies that out of everything we predicted as positive, which is no-shows, how many of them are true? And how many of them are correctly predicted as positive, no-shows, right? So a simple example, let's say you have a total of 100 patients predicted by the doctor to be no-shows. That's everything predicted to be positive, no-shows. Okay? Among those 100 patients, 63 of them are really no-shows. The remaining 37 was incorrectly predicted to be no-shows. And then precision tells you that the metric precision tells you that precision of positive labels or no-show prediction is 63%. Right? And that's applying the formula. And I mean, I have some discrepancies in terms of number because I kept using different examples and didn't get to unify all those numbers here. But the idea is the same, right? So I mean that here, this number 65, I mean that 65% of the no-show predictions, everything predicted to be no-show, out of this all no-show records, 60% of them are actually correctly predicted. And that's the prediction, the precision of your prediction for no-shows. Right? And then if you look at this number, 0.55 here, right, that's the precision for zero labels, precision for shows, right? So for among all those patients predicted to show up, only 59% really showed up. Okay, that's the meaning of precision for the different class labels. Do we have any questions? Okay, so I mean, it's I tend to find it to be slightly confusing every time I try to remember the meaning. But anyways, so afterwards, if you look at the definition and the numbers, once again, I think it will become more and more clear. But there's another concept called recall, which I think is a nice complement to the precision metric. So let's look at this number. Recall for the one labels, recall for no-shows. What does that mean? So let's quickly go to the formula. The formula is here. It's the ratio of true positive over true positive plus false negative. And let's look at the denominator. True positive plus false negative. I mean, that's everything that is positive in reality, right? I mean, true positive is predicted to be positive, but it's true, so in reality they are positive. False negative was predicted to be negative, but it's false, so in reality they are also positive, right? So in reality, all those positive realizations or the positive outcomes, among this many of them, how many were correctly predicted to be positive, right? I mean, this may be still a bit abstract, but let's put it into context, right? Let's say you predicted that a total of 100, not predict, so this is recall, so it's more like recall what actually happened in reality, right? So out of 100 patients, let's say in reality, they actually didn't show up, so they are ones, and they are no-shows. Out of this many patients, let's find out how many of them are captured in your prediction as no-shows. Right? If 53 of them are predicted to be no-shows, out of the total 100 who are actually no-shows, then your recall rate is 53%. Right? I mean that for those no-shows, you were able to capture 53% of them in your prediction. Again, maybe slightly confusing when you start to deal with it, but I mean, I guess the meaning will become much more clear, right? So recall is that you try to recall how many actually didn't show up after all the appointments are done, and then count how many inside this segment population actually were predicted correctly as no-shows, right? And now this number, the other number, 67% as a recall value for the label 0. I mean that for all those 0 labels in reality, I mean for all the patients who actually showed up in reality, 67% of them were correctly predicted to show up. Right? So that's the meaning of recall. Okay, so I guess it's maybe a bit confusing in the beginning, but I think it will be okay later on. Now, that's precision and recall. Okay, and there's also something called F1 score, but this one is, I mean, look, it's very easy. So basically, you have a precision for, let's say, for class 0, and also for class, also for recall for class 0, right? And F1 score is some kind of average of those two numbers, right? So it's precision recall reflect different aspects of the performance. So how about we do an average, right? So it's not simple average. is something called the harmonic mean. The formula is here, okay? But it's not too important. The idea is that it's some sort of average between recall and precision to reach a comprehensive, more comprehensive measure. And so this is the F1 score. So this is the F1 score, and same thing, for the F1 score corresponding to the row starting with 1. So that's the F1 score for the no-show records, right? It's again an average, harmonic mean average of precision and recall for the same label of 1. Right? So that's how it works. And accuracy is something really simple because you just count how many of the predictions are correct out of the total number of predictions we have made in the test data set. So the denominator is just the size of the testing data set, assuming that you have made a prediction for every single record in the testing data set. And the numerator is to count all those correctly predicted, right? Either true positive or true negative. Okay. So this is the accuracy, only in one number here, right? One thing to quickly note, if you look at support, there's a column called support. And support is not a metric, okay? 165 is simply how many labels in the testing data set is 0. Just counting the number of zeros, okay? And 179, that's the support of 1 labels, or how many 1 labels are there in the testing data set. And those are not metrics, those are just counting, right? And macro average, looking at this row, again, very simple. What is macro average? Well, this number, 0.62, is the average, simple average, of the two precision values for 0 labels and 1 label, right? Just an average, nothing else. And similarly, the 0.62 as the macro average for recall is again the average of the 2 recall values. Okay, and this macro average of F1 score is the average of the 2 F1 scores for 0 and 1 labels. Okay. Pretty simple. And the weighted average is actually also the same. It's also an average. Let's say for the precision column, the weighted average is also the average of the 2 precision values, but then they are weighted by the support, right? It's weighted by the number of observations under each class. So that's how it works. And same thing for the remaining weighted average values for recall F1 score. It's still average of the top 2 values of the same column, but you are weighting them by the number of occurrences in terms of the number of zeros and number of ones. Okay. Anyways, so it's a bit, I guess it's a bit, sometimes can be a bit confusing, but I have included rather detailed explanations in the slides. So I would recommend that you do take a look at those explanations if things are not crystal clear in your mind, for how to interpret all those performance measures. Okay, and let me quickly mention some other metrics that didn't show up in the classification report or the confusion matrix. One thing is the true positive rate, but this is very intuitive, right? So it's the rate of true positive, predictions out of the total actually positive outcomes in reality. But this one is also, has several names. It's also called sensitivity, but it's actually the same thing as a recall, right? If you compare the formula, it's also the same thing as a recall. It's just to see how many true positive predictions you have made out of the actual positive outcomes. So nothing new, same as a recall. And this the false positive rate. Look at number of false positive predictions and compare that with the total number of records where you either predicted as a false positive or true negative. Right? So this time you are comparing the false negative with the actual negative outcomes. Right? So for those positive predictions, how many of them were predicted wrong, and you compare that with the total number of negative outcomes. So that reflects something called the false positive rate. Again, it may take a while to get a better picture of this. So I'm gonna quickly skip that part. And finally, there's something called the ROC curve, the receiver operating characteristics. I think some of them may encounter similar concepts before. So once again, we're not gonna dive into the details, but let me just show you the plot and quickly explain the meaning of this plot. Okay? So for this logistic regression model, remember we first can generate the probabilistic predictions, right? So for any record, we can predict the probabilities of that record belonging to the 0 class or 1 class, negative or positive class. Right? And then by default, we use 50% as the threshold. So if the chance of being positive exceeds 50%, we predict 1. Otherwise, we predict 0. But of course, you can totally actually adjust the threshold level. You can use the threshold level of 20%, 30%, 40%, 50%, or any percentage value. Okay? However, the outcomes of using different thresholds will be different. And this plot says that while you are trying different threshold values, the true positive rate and false positive rate will be different. And eventually, I experiment on all the possible values of threshold for determining the binary predictions based on the probabilistic prediction. And then for each trial, I can use a point to represent the true positive rate and false positive rate by using its coordinates on the plot, right? So eventually, this red curve represents the different possible true and false positive rates you get for different experimentations based on different threshold values. So this red curve here is called the ROC curve, receiver operating characteristic curve. And all we want to know is that how that will connect to the performance of the model, right? So, and this leads to another concept called AUC, area under the curve, right? So the total area under this red curve is called AUC, and that's a score. Okay? So question, AUC can be, if the red curve is very close to the bottom of the square, and then AUC is 0. Right? If the red curve is pushed along the top left direction, eventually overlaps with the ceiling of this square, and then AUC is equal to 1, because this is the unit square. Right? And false positive and true positive values can only be between 0 and 1. So AUC value can be 0 or 1 or somewhere in the middle. Right? So question, if we have a higher AUC score, do you think it's indicating good performance or bad performance? Do we want the AUC score to be high or low? So what do you think? Yes?
Yeah, you don't want it to be close to the 45-degree line. We kind of want it to be high.
Yeah, exactly, right? So it's actually the case that you want to stay away from this 45-degree dashed line. Why is that? If you're on, yes, please.
Yeah, it's just because, obviously you're gonna have more positive than like false flags, right?
Exactly.
If you're staying as far away as possible.
Yeah, because that's very good. Because on this line, it's 45 degree, right? So the true positive is equal to the false positive rate, right? Ideally, I want to have higher true positive than false positive, right? So I want to move upwards. If I move upwards, and then I'm staying more away from low true positive rate than false positive rate. Right? So on the line, we have equal false and true positive rate, so it's basically a random guess. I want to be better than random guess, so I want to locate as much as possible above this dashed 45-degree line. Right? In the ideal case, the red line should be on the top. It means that the true positive rate should always be 1. That's the ideal case. Right? So in that case, the AUC score will be 1. Right? So that's why I want the red curve to be pushed toward the top. Because if it's pushed toward the top, the true positive rate is going to be higher than the false positive rate. And then a larger AUC score is going to be more desired. So I think we have just just a few moments to finish the codes for the RC curve and also AUC score for this notebook. So let's quickly finish that, and then we can move on to the second break of today's class. Again, I will not actually spend too much time on explaining the code, but because I think the code actually explains itself, right? So it's basically I imported a function from the metrics library. The purpose of this this function or this module is simply to display the ROC curve. Right? So the name is simply ROC curve display, so you know what it means, right? So and then we're gonna use the pipeline. That's the basis of our prediction based on the fit-in model, right? And then we have the testing data, because based on the testing data, you generate the predictions and compare them with the actual outcomes in the testing data. So a lot of things were abstracted away here, but all we need to know is that by doing this command, we can get a curve like this. I mean, it's not a red curve. If you want, you can change the color to red, but the curve is the ROC curve, right? Receiver operating characteristics curve. And the idea is that we want it to be as close to the top as possible of this unit square. Okay? And it already shows you the AUC score, which is 68%. But then there's a command which is going to be maybe sometimes more faster in terms of giving you the result, right? So so we can. I mean, again, this is pretty straightforward. So let's not spend too much time on explaining it. So, but with just a very quick comment. Okay. So this AUC score is calculated by this function called ROC AUC score from the metrics module of sklearn. And inside the score, we include two components. One is the actual labels in the testing data. The other is the probabilistic prediction on the positive outcomes, something we have seen before, right? And then there's, again, a lot of things were performed behind the scenes, but this number is the AUC score out of this command. Right? So at this point, maybe... Yeah, one more thing, again, very quickly, not to spend much time on explaining because it's actually, I think it's relatively straightforward. So there's a command called accuracy score, gives you directly the accuracy measure, something we also showed you a formula about, right? So this is all those different metrics. One observation is that if you look at the classification report, right, and the percentage values for precision, recall, and later on also the accuracy and also the AUC score, they are not that high, right? Typically in the 60% range. So, I mean, one conclusion is that the prediction outcomes or performance is not that surprising. I mean, not impressive, I would say. Right? So it's not that satisfactory for this method. In many cases, it may not be the fault of the model, right? It doesn't mean it's not a good model. It may be just indicating that the problem is difficult, right? So predicting patient to be a show or no show, that's usually not that trivial, right? I mean, what we can conclude is, first of all, it's better than a random guess, right? Because for random guess, you will have all those values equal to 50%. Right? 50% of chance is actually equal to a random guess, right? So, but it also suggests that potentially, if you use other methods, possibly you can do better. And the idea is pretty simple. We just look at what's near the data record and see what observations we can make for those already observed records that is somehow close to the one you are trying to make predictions. Okay, so the idea is pretty simple. It's a distance-based model because we are trying to find the close-by records. So we have to define a certain distance, and usually it's a Euclidean distance, but we're not going all the way back to all those mathematical theories. Instead, all we need to know is that we're going to just check the close by records to the one you want to perform prediction about, right? So a very simple example, let's say we have a data set, we observe different individuals, we know their age, we know their annual income, right? And then we also have a column of their profession. I mean, some are office workers, some are YouTubers, some are managers, and all different possible values. And let's treat the profession column as the target variable. So want to predict someone's profession based on their age and income. For this part, there's no, we don't have any coding because this is just supposed to be an illustrative example, right? Now, I intentionally included only two features for this example because we can easily plot a two-dimensional structure. Right? If it's high-dimensional, the idea will be the same, but the plotting will be difficult. Right? So let's plot all those points regarding the two features, age and income. Right? So we have this figure here. The horizontal axis represents ages. If you move from left to right, it means that the corresponding ages of the corresponding data points will be increasing. Right? So let's say this point here apparently is corresponding to a much older individual than this point here. Okay? And the vertical direction will be the income. The higher up, the more that person earn as their annual income. Right? And all those black and the green and the blue dots, and those are the observed data points in the data set. Right? For each point, we have income, we have age, and the color represents the different, profession or jobs of those corresponding individuals. Right? Black is YouTuber, green is office worker, blue is manager. Okay, it's color coded. Now, this is our data set, right? I mean, for every point in the data set, we already know their profession. But how about I point randomly at a location? For example, this red cross here, it's not in the data set, right? But let's say this person is relatively young, maybe let's say 18 years old, and the annual income is somewhere, maybe let's say 100,000 per year, right? And can you guess the profession of that individual? So that's the task. So applying the idea of k nearest neighbors, of course, we need to determine how many nearest neighbors we want to use, right? So for example, let's use 5 nearest neighbors, and the number of neighbors we want to use is going to be a hyperparameter that needs to be determined before you apply this model, okay? So for this red cross representing an individual record, let's say we're looking for using the 5 nearest neighbors, and then simply we need to identify the 5 closest points to this location, right? And turns out, apparently, it's in the middle of a bunch of black dots, and black points represent YouTubers, okay? So all those 5 nearest neighbors are YouTubers, and then this individual, represented by this red cross, who is not in the data set, if you have to predict their profession, I guess, according to this model, we're going to predict also YouTuber, right? Because the neighbors are all YouTubers. Now, another example. Let's say I want to predict an individual represented by this new red cross, the red cross in this new figure here, right? And the horizontal value will be representing the age, and the vertical value will be representing income. So in this case, again, we want to look for a certain number of neighbors, depending on what model you're using. Let's say we're using 10 nearest neighbors, right? So for this red cross, we're going to identify 10 closest points. Now this time, let's say it is for those 10 closest neighbors, 8 of them are blue points, and 2 of them are green points. If you look at the color coding, blue represents office worker, and green represents managers, right? So let's quickly go back to check. Oh, sorry, the other way around. Green is office workers, and blue is manager. Anyways, if you have a location here represented by the red cross, and turns out 8 of those neighbors are managers, 2 of those neighbors are office workers. So what would you predict? If an individual is located here in terms of age and income, 8 closest neighbors are managers, and two neighbors are office workers. So what would you predict as the profession of that individual? Yes, please. Manager, I guess it's a majority vote, right? So because more neighbors are managers than office workers, so based on the principle of a majority vote, maybe if I have to predict the profession of that individual, maybe also a manager. But the good thing is that not only I can provide a label as a prediction, but in the neighborhood, I have 8 managers versus 2 office workers. You can also provide a probabilistic estimate, right? So 8 out of 10 of the neighbors are managers. So maybe for this location, I can say that with 80% of chance, that person is also a manager. Right? So not only you can provide a deterministic label prediction, but you can also come up with a probabilistic value to measure the likelihood of that person being a manager. Okay? So this is the k nearest neighbors. Choice of k actually matters, right? I mean, of course, usually we don't start with a good guess of k values. Do you need to use 2 nearest neighbors, 5 nearest neighbors, or 100 nearest neighbors? I mean, in the beginning, we never know, right? In some problems, it's better use 5. In some problems, maybe better use 100, right? So this is, again, something called hyperparameter. But the idea is that if you use a small k, it means that you're only looking at the value of the nearest one neighbor, right? I mean, we know that's not very reliable to make a prediction only based on one other data point, right? So there's going to be a lot of variance because it's unreliable, right? Things can change differently for different locations in the plot. Right? So if it's too small, it's not a good idea, right? If it's too large, then you have a lot of points based on which you are making the prediction. But what's the downside of using, let's say, 1,000 neighbors? Well, let's say you're using maybe 1 billion neighbors, right? And basically you are using all the points in the data set. And then it's meaningless because, well, it's no longer nearest neighbors, right? You're including every neighbor. And some of the neighbors are very far from you, so they give you biased information. So it's not a good idea either. But where is the sweet spot? We never know. So, I mean, you probably heard of this concept called hyperparameter tuning. So just to change this hyperparameter of k, how many meters you want to use, to see how the testing error changes. Right? For a specific problem, you can always arrive at a reasonable testing error by adjusting the k value, and that's the one you want to use. Okay, so that's just some background information. One important point is scaling. Okay? So scaling is more like a standard procedure as pre-processing. Sometimes it doesn't matter, but sometimes, like in k and n, k nearest neighbors, it matters a lot. Right? My example here is that, for example, you consider the distance between 2 pairs, right? Because you're looking for nearest neighbors, you need to figure out which neighbors are closest. Okay? If you are looking at the 2 individuals, one with an annual income of 50,000 and age of 30, one with the annual income of 65,000 and 60. I mean, the annual income is on a much larger scale than age, right? I mean, age can only be up to, I don't know, like the 80, 90, 100 at most, right? But annual income can range from very little, close to 0, to maybe 1 million or even 1 billion for some extremely rich person, right? So if you do the distance calculation, it will be dominated by annual income, right? Because the numbers are so large. However, the gap of age is only 30. Looks very trivial, but 30 years in age is very significant, right? So then, if you only look at the magnitude of those numbers, it gives an unfair advantage of one feature, which is the annual income, in terms of how they will influence your prediction outcome, which is not good, right? So that's why for the prediction models based on distances, like k nearest neighbors, it's a requirement for you to perform scaling. Okay, so for logistic regression, it may not be that important, but for KN, it's extremely important.